Okay, have a quick look at this example 8.4. I know I keep saying have a quick look and then it turns out to be a long video, but okay, the intention is always something quick. Okay, in the previous video, remember that we discussed impending motion at some points of contact. Impending motion at some points of contact. That was what I discussed here, impending motion at some points of contact. So what did I say? Is that when you have impending motion at some points of contact, you assume impending motion at one point and not impending motion at the other point, and you solve your problem. And then you assume impending motion at the other point and not at that point, and you solve your problem again, and you compare your results, okay? So here we are going to have a look here in example 8.4 at impending motion at some points in contact, okay? So let's try to fly through this. Very simply, what you got here is your beam, you got a distributed load, and you got this little, what do they call, like a wedge or something like that. Post, they call it a post, okay? There's a post BC, little wooden post that's holding this beam up. You've got a distributed load, you've got a pin connection at A. All right, so the first thing essentially what we need to do is we draw a free body diagram of this. Actually, that's not the first thing you do. The first thing we do is we need to read the question. That's what we need to do. And you've got this set up and you've got this force P that's being applied on the post. And this force P wants to pull this post out from underneath this, this beam, okay? So it says here, and it's got a coefficient of friction of 0.2 there between the beam and the post there. It's got a coefficient of friction of 0.5 over there between the post and the floor, okay? And there's this applied force P. It says determine the force P needed to pull the post out from under the beam, okay? Determine the force P needed to pull the post out. Now, what do you see from this? You see that there are two possibilities. The one is that the post could slip there, and you could, let's try to draw this. The one is if there's the post, and you've got this applied force P, and there's the beam, okay? The one is that this could slip and it could move like that. So the beam could, the post could move like that, and you could pull it out in that way. That's the one option. And there's no movement at this point. Or the other one is that there's no movement at this point and you pull it out like that from beneath. Okay? So there's essentially two scenarios we have, two cases, two assumptions. All right? So what do they do first? Well, they just do standard chapter 5 stuff where you reduce that to a single force of 800 Newton and you do your standard chapter 5 equilibrium equations and you solve for this normal force, okay? So sorry, let me just wait until it focuses. Come on, there we go. So the whole idea of this free body diagram and the equations of equilibrium of this section are simply to find that normal force. That's all we wanted to do. So it says here, the free body diagram of the beam is shown in figure 810b, applying some of the moments about A equal to 0, we obtain the normal force B. Now, why did we want to obtain the normal force? Why is that so important? Well, we know that our frictional force is equal to mu s times n. And that normal force that we see there is essentially when we look just at the beam, at this post, I mean, that's the that's the normal force coming down there, okay? And it is equal to 400. All right, so this whole section here is just to get us to the point where we can solve our problem. Okay, so now let's do a free body diagram of this post. We have our normal force, we've got our applied force P, we've got our FB, that's our frictional force. Remember, the frictional force always opposes the direction that we want to move the beam, the post, and there is FC. Okay, and we've also got our reaction NC there. And we've got 0.75 there, and we've got 0.25. All right, so there's our free body diagram. That's step one, free body diagram. Guys, by the way, when I walk around in class and I talk to you, I don't see you guys drawing stuff. Engineers communicate with drawings. Do a lot of drawings, communicate, draw everything you can, okay? Well, yeah. So now, this is our first step, free body diagram. Now let's set up our equations of equilibrium. Sum of the forces in the x equals 0. We've got P minus FB minus FC equals 0. Sum of the forces in the y equals 0. Very simply, we've got NC minus NB, which is 400, equal to 0. And we take sum of the moments. And I'll just copy them. They take sum of the moments about that point there. Let's call it C. So what we get then is, if we take counterclockwise as positive, we got minus P times 0.25, right? The moment of P, like that, it's clockwise. And we then get plus FB, it's going anti-clockwise, times 1, gives us 0. So these are just simply our equilibrium equations that we set up based on our free body diagram. So that's all pretty standard stuff. The only thing we needed to do first was we needed to calculate this normal force, which we calculated from this initial setup there. Okay? And we drew our free body diagram and we set up our equations of equilibrium. Now this is where we apply this idea of impending motion at some points. Now we need to say, let's assume let's see what they do first. They say, let's assume the post slips at B and rotates about C. Okay, so what that means is, let's draw this here. It slips at B and rotates about C. That means we've got impending motion at this point and not impending motion at that point. So remember, if we draw this graph like that, so remember guys, impending motion at some points. So we've got impending motion. We assume impending motion at that point and not at that point, which means that point we're over here on our curve, but that point we are somewhere here on our curve. All right? So let's assume that. So assume impending at B, but not at C. Okay? So what does that mean? It means that we can use all our equilibrium equations. Remember that we can use all our equilibrium equations for this, but then we can only use FB is equal to mu B NB as an additional equation. That FC is just a straightforward unknown equation. It's an unknown force which we solve using equilibrium equations. So there's that FC there. But FB, we are assuming that it's slipping there, so we know that FB is equal to mu times N. All right? Which then equals what? 0.2 is the coefficient of friction and NB is 400. That equals 18 Newton. I'm not going to do all the calculations, but if we put that now into there and we solve all our equations, the textbook shows us that we get a force P equal to 320. FC, that's the friction equation at point C. We solve for P equals to 320, FC is equal to 240, and the normal force which we calculated before is 400. Okay, so we've assumed that we have impending motion at that point. So we calculate FB and we calculate all our unknowns like this. But now, what is interesting is that we've calculated FC to be 240. But the maximum that FC can be is mu CN, right? And what is this? What is that? It's equal to 0.5 times 400, which is 200 Newton. So the maximum frictional force that can occur there is equal to mu N. Why is that? Because that's based on this. The maximum friction force that you can get is equal to mu times N. And the coefficient of friction at that point is 0, come on, man. I don't know why this doesn't focus that well. There we go. So the maximum frictional force that we can get at this point is equal to mu times N. And mu is equal to 0.5 and N is equal to 400. And so the maximum force we can get is 200. But we've calculated based on this initial assumption that FC is greater than 200. So clearly, this first assumption is wrong because we've calculated a friction force higher than the maximum friction force that can occur there. All right? So then the next thing we look at is then impending motion at C and not at B. Okay? So that then means FC is equal to mu C NC, which is then 0.5 times that 400, which is actually 200 Newton. Then if we take this value and we put that into there and we solve, we end up with this range of answers. P equals 267, the normal force, FC, which we just calculated, and FB then is 66.7. Okay? So what you notice here is that the P there is 267 and the P there is 320. So as you're slowly increasing the P, it's going to hit 267, and as it hits 267, FC, there's going to be impending motion at FC. It's going to slip from at that point, but the point at B will still be to the left of this curve, and we will have rotation about B and we'll have slipping at C. Okay, so I hope this has helped for us. This is a nice example of impending motion at some points of contact. Cheers.